rolling. Okay, so there we go. Bye-bye toolbar. We are finished the kind of theoretical part of our chapter 4, 4.1, 4.2 lesson. And now we're going to get into the part where we actually have to, like do some math, the skill part. I kind of spent, like a class and a half playing with this. At the end of the day, all you have to really know are the names. You have to know the difference between what an irrational number is and isn't. And that's what the first examples kind of focus on. So, determine whether or not each number is rational or irrational. And obviously the easiest way to tell is, of course, to just look at it and go, could I make a fraction out of this? I mean, that's it. That's the easiest way to think about it is, could I make a fraction out of that number? Okay, and so let's see. Let's think about it. Can you make me a fraction that equals negative 15? Well, the most simplified one you could make would be, let's see, did my pen just turn off when I auto-rotated my screen? I think it did. Hang on, let me get back to my pen. There we go. Would be negative 15 over 1. There. That's a fraction, right? It's an integer over an integer. It equals negative 15, so that means it's a rational number. I was able to express it as a fraction. I could have said negative 150 over 10. I could have said negative 30 over 2. There's infinite ways I could have expressed it, but the simplest is negative 15 over 1. If I can do that, it's rational. Now, can I make 1.21 into a fraction? Well, it's a terminating decimal, so that makes it 1 and 21 hundredths, which would make it 121 hundredths. That looks like a fraction to me, so it's rational. Now, how about the square root of 100? Well, yeah, the square root of 100 is 10, and by the same rules as A, 10 over 1 is a fraction, therefore it is rational. 6/11ths, it's already a fraction. Rational. Ah, what about that guy? Well, when you square root a fraction, you're supposed to remember from grade 9 that you can square root the top and bottom separately. So you don't have to actually do the divide first and figure out what decimal that is or whatever. You can think of that as 7 over 4, which is a fraction just like in D, so that is definitely a rational number. Okay, with me so far? Finally, rational, 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 stop. That is not a rational number. How come that is not a rational number? Well, look back at the rules. Irrational numbers are the square root of any non-perfect square. And 49 16ths is a perfect square. It's 7/4 squared, right? What was the other one that was on here? 100 is a perfect square. It's 10 squared. 18 is not a perfect square. If you square root 18, what's going to happen to you? Let's ask our calculator. We're going to go, oh, calculator, wake up. Oh, calculator, what happens when we square root 18? And the calculator is going to say to us, well, it's 4.24264. Now, I look at that and I go, well, maybe it's 242640687 repeating. How do I know that doesn't repeat? Well, I know because I know the rule. The rule being that if you try square rooting a perfect square, you will not. If you try square rooting a perfect square, you get a whole number. If you try square rooting a non-perfect square, you get an irrational number. So this one is irrational because 18 is not a perfect square. Yeah, perfect square. Now, here's something that you used to do back in grade 9. They used to make you do this with fractions and decimals. Now let's do it with irrational numbers too. Can we put all of those numbers on a number line? Ooh, interesting. Okay, so let's see. What do we know about the square root of 23? Well, I know the square root of 16 is 4. I know the square root of 25 is 5. So by that logic, the square root of 23, it says 23, is somewhere between 4 and 5. I'm thinking it's closer to the 5, since 23 is closer to 25 than it is 16. So I'm thinking it's maybe, I don't know, 4.7, 4.8. Actually, again, here's something that used to be in the grade 9 curriculum. I think it actually still is, but almost no teachers ever get to it. You want to know a good way to estimate what the square root of 23 is to go, okay, well, if 16 is this, or sorry, let me say that again. If the square root of 16 is 4, so if that's 4, and the square root, so let's go 17, 18, 19, 20, 21, 22, 23, 24, 25. Pretend that all those are the same distance apart. Here, let me move it over a bit. 25. And I know that the square root of 25 is 5. Well, then where would the square root of 23? So this will be the square root of 17. This will be the square root of 18, 19, 20, 21, 22, 23. So this is the square root of 23. So there we go. So this is 4 and 1, 2, 3, 4, 5, 6, 7 over 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's 4 and 7/9. That's my estimate. So there we go. So that's my estimate. So 23 is approximately 4 and 7/9, where that's about, again, the 9 trick tells us that that's 4.7 repeating. So on the number line, root 23 is, did I say 4? Why did I say 4? Oh, yeah, that's right, 4. Yeah, that's right. What am I thinking? Sorry, I'm looking at the next numbers and getting confused. 4 and 7/9. So 4, and so if that was 9 units, 7 would be about there maybe. So there we go. There's my root 23. Right there. Root 20. That's a 3. It's an ugly 3, but it's a 3. We love it anyway. Okay, so there we go. That's how I know that. Now, every once in a while when I show that to students, they go, oh, that's a neat way to estimate a square root. And then every once in a while somebody looks at that and goes, wait a minute. Wait. Why isn't that exactly the right answer? I mean, you counted on a number line. If this is 16 square rooted, which is 4, and this is 25 square rooted, which is 5, why isn't the square root of 23 exactly 4 and 7/9? And that's a good question. And the reason is because the distances between the square root numbers are not really linear, and they're not really the same distance apart as you go. I can kind of prove that to you if I show you using, say, a graphing calculator or something. In fact, here, I'll just bring up a graphing calculator really quick. Okay, come on, graphing calculator. Fine. Graphing calculator. Oh, see, now this is just going to, there we go, go away. There, if I click it with the mouse, it goes away. Let's remember that from now on. If I say, okay, I would like to do a graph of all square root numbers. So I'm going to graph y equals, and oh, you can find square root in this this little keypad full of functions and stuff. In fact, it's right there. But you know my favorite way to find it is to type in SQRT, and look at that, it knows right away that you want a square root. So y is equal to the square root of x. Notice that's not a straight line. So the actual distance between 2 on this line, which is the square root of 4, and say, so 2 on this line, which is the square root of 4, and 3 on this line, which is the square root of 9. Maybe, there we go. So 2 on this line, which is the square root of 4, which is right there. Why don't I actually put the points in? 4, 2, and so there's that one. And then the next perfect square that's going to be a nice whole integer for us. You know what? I'm actually missing one, obviously. Why don't I put the first one down? Isn't 1, 1 going to be nice and perfect integers for me? There we go. So notice that the distance from here to here is not going to be the same as the distance to the next one. What's the next one that will be a nice perfect, hits the integers on the grid place? Well, it'll be when x is 9 and y is 3. So let me type that in, 9, 3. Notice, can you tell by looking at it? Maybe it's hard to tell here, but along the number line horizontally, this distance is smaller here than it is here. And you could really see it to the next one, because the next perfect point that hits integers will be 16, 4. And now you can really see it, right? That distance is clearly a wider distance than the first two. So the space between perfect squares is growing, which means even the space between non-perfect squares will be growing. So that means that this estimation method gets worse and worse the bigger, or gets less and less accurate the bigger the numbers are. It could never be perfectly accurate. So hopefully that makes some sense to you. But it's not a bad way to get an estimate. Like again, let's go to the calculator. Oh, calculator, what is the square root of 23? Not bad. What is 4 and 7/9? 4 plus 7/9. Well, I actually already know this. It's 4.7 repeating. So it's only off by 2/100ths. That's pretty good. A little over 2/100ths. Okay, so anyway, that was only the first one. Let's keep going. Okay, the square root of 9 is easy. The square root of 9 is 3. So the square root of 9 is right here. Negative 5 halves. Okay, I could think of that if you like. Negative 5 halves is negative 2 1/2. All right, so negative 2 1/2 is that way. Okay, so there's negative 5 halves. Okay. All right. Don't forget when you're counting negatives, the fractions go negative too. Here's what I mean by that. This is what, after many, many years of teaching grade 9, where you were supposed to learn how to put things on number lines in grade 7, 8, and 9, I'd get this. Kid would go, oh, I want to do negative 2 1/2. So they'd count like this. They'd go negative 1, negative 2, and 1/2. And they'd stop there. And I'd say, well, isn't that negative 1 1/2? No, I say I went negative 2, then I went 1/2. So what, the half part is positive? That doesn't make any sense. Anyway, make sure you don't do that. The cube root of 28. Ooh. Anybody know their perfect cubes? Well, 1 is a perfect cube because it's 1 times 1 times 1. 2 is a perfect cube because it's 2, or sorry, let me say that again. 8 is a perfect cube because it's 2 times 2 times 2. 27 is a perfect cube because it's 3 times 3 times 3. And the next perfect cube is way up there at 64. So the cube root of 28 is going to be way closer to that number. So I'm thinking it's like it's probably so close to being 3.1. Those two dots would be like conjoined dots. So that one there would be the cube root of 28. Feel free to use your calculator. I have a feeling it's probably even smaller than 0.1. It's probably 3.0 something. 3.08 maybe, 3.07. Oh, see, now I'm curious. I want to see. How close is my estimate? Am I right? Is it not as big as 0.1? How do you do cube root on a calculator? Anybody know? Well, on my calculator, I have a couple of options, actually. I can have I can change, what I can do is I can think of a blank root as, where is that? Is that what this is? Hold on a sec. I can't see because it's too small. Oh, good heavens, no. That's my times 10 to the button. Oh, there it is. It's right here. It's my blank. It's actually in math. That's right. That's where it is. So I can go to math and I can say, oh, there we go. Cube root. So 4. My cube root of 28. And what did I say it was? I think it's 3.08 maybe. Oh, I was actually way too high. It's 3.03. There we go. 3.03. That would be basically so far on top of that dot. Those two dots would merge to be like super dot. All right, one more. Negative 2.3 repeating. Well, this is where I have to know my fractions and know that that's negative 2 1/3. So negative 2. Now, hang on a sec. If this was negative 2 1/2, where's negative 2 1/3? It's not as far over. So that one goes there. That one is negative 2 1/3. So there we go. We expect that we can take your sense of number and your ability to count that you were supposed to learn in junior high, like where do fractions and decimals all belong on a number line, and you can now add to that, where do irrationals go on my number line? Because you can estimate them, you could take out your calculator and figure out what they are, and then put them on a number line. So there's one thing that we might ask you to do. Put them on a number line. Next, let's move on to 4.3. So in this section, a little bit of notes here. In this section, we learn the algebraic / arithmetic rules for working with radicals. And I'm going to say that radicals follow the bedmass rules of B, which of course, remember in bedmass stands for brackets. Those of you from other countries might use the letter P for parentheses, but it's the same thing. Okay, I'll get back to that one in a second. Radicals follow the bedmass rule for B for brackets and E for exponents. Radicals are both brackets and exponents at the same time. That's going to be a weird idea to get through your head, but we're going to prove it to you in a minute. Okay, somebody was asking about the cube root of 28. So what does cube root mean? Well, square root of a number is the opposite operation to squaring, right? Square means what number times it means take this x number and times itself, right? Whereas square root means I have some number times itself makes x. So that's what square root is. Cube root is the opposite in terms of the cube root of x means I have some number that if I took 3 of those numbers, times them all by themselves, I'd get x. So if I ask for the cube root of 27, I get 3. Why do I get 3? Because 3 times 3 times 3, get it? 3 of them together make 27. The next perfect cube root is 64 because 3 4s multiplied together make 64. So if I'm asking you for the cube root of the number 28, obviously it has to be a decimal between 3 and 4. And it has to be much, much closer to 3 because 28 is a much closer number to 27 than it is to 64. So I know that on some sort of number line, if this is the cube root of 27, which is 3, and this is the cube root of 64, which is 4, the cube root of 28 would be right there, and then I'd have 29, 30. In fact, 64 minus 27 would equal, let's see, 14 minus 7 is 7, and 5 minus 2 is 3. There'd be 37 other numbers that would have perfect cubes between there and there. And this would be the first one, right? This would be 28 cube rooted, 29 cube rooted, 30 cube rooted. So I think that a good estimate, and again, it won't be perfect because this scale isn't really linear, but it would be a good estimate to say that the cube root of 28 would be 3 and 1/37. And just for fun, let's see how close that is. Let me go back to my calculator. And, oh, there I still have it. The cube root of 28 is 3.03. What is 3 and 1/27? Or no, sorry, it was 37th. Oh, crap. Go back. 3 and 1/37. Let's see how close this is. There you go. Again, I'm off by 1/100th. 3.03 versus 3.02. So it's pretty close. But it ain't perfect, and it can't be. I don't know. Americans, actually, it's more of a European thing, more of the British. I mean, listen to the word. For those of you wondering what I'm talking about, in the comments somebody says Americans would call it PEMDAS because they always put multiply before divide. It doesn't really matter what order you do them. If they're left to right, you just go left to right. And they use they use E for exponent. The British use I for indices instead of E for exponent. And the British are the ones who tend to use the word parentheses. I mean, listen to the word parentheses. It's kind of that's the parentheses. Very, very British sounding word. But anyway, moving along. Let's see if we can blow your minds a little bit. Where do radicals fit in? Well, first of all, there's a multiplication property of radicals. And here's the multiplication property. It says that if you have the square root of A times the square root of B, you have the square root of AB. Hey, does that look familiar to you? Have you ever seen a rule like that before? Yeah, you have. You saw it in grade 9. You saw it in something called the power of a product rule. that said that you can distribute a power into a product. So for example, 2 times 3 squared is the same as saying 2 squared times 3 squared. Prove it if you don't believe it. 2 times 3 is 6, 6 squared is 36, 4 times 9 is 36. Notice that that rule would not work for a sum, right? Is this a true statement? Like heck it is. 2 plus 3 is 5, 5 squared is 25. 4 plus 9 is not 25, it's 13. Nope. That, by the way, is how come we had to learn how to FOIL, right? Back when we were doing algebra, you can't just say, oh, that's x squared plus y squared. No, it isn't, because take a look. Arithmetic doesn't work that way. So, back over here, this is me treating radicals like an exponent, because it's basically the exponent rule for powers. So, I'm going to say, for example, the square root of 4 times the square root of 9 is like saying the square root of 36. It's the same thing. They're both 6, right? 2 times 3, 6. Square root of 36, 6. It works. And I'm going to say note, and then I'm going to change to red to make sure we all see that this is going to be something that's wrong. Don't ever do it. The square root of a plus the square root of b does not equal the square root of a plus b. Not possible. Try it if you don't believe it. For example, is the square root of 4 plus the square root of 9 equal to the square root of 13? Is that a true statement? No, obviously it isn't. 2 plus 3 is 5. 5 times 5 does not make 13. Okay? So that's the multiplication property of radicals. Okay? The other thing we're going to write about the multiplication property of radicals is we're going to say that if we had something like a times the square root of b, I can rewrite that as the square root of a squared b. And that's kind of the more important property. I mean, it's basically the same property as over here, but that way is more important because it allows me to simplify radicals, because I can use this property backwards. If I notice I have this situation, I can turn it into that situation. And we saw a little bit of this last chapter when we were doing the distance formula between 2 points. The square root of 48 is equal to the square root of 16 times 3. Why 16? Why did I single out 16? 48 can be broken up into multiplies all kinds of ways. It's 1 times 48, and it's 2 times 24, and it's 6 times 8. Why did I pick 16 times 3? Because 16 is the largest perfect square factor in the number 48. So that means that I can rewrite this as the square root of 16 times 3. I can use this rule, either you can look at it here or look at it there, and say that, aha, it's the square root of 16 times the square root of 3, which is 4 root 3. And this, to a mathematician, is simplified. I know it looks like it's more complicated than the square root of 48. I mean, sure, 48 is a bigger number than 4 and 3, but at least it's just a single number. But to a mathematician, this is a simpler answer. So that's what we're going to do. Is that not a derivative rule? Yes, I can basically say that this rule kind of derives from that rule, if you would like to think of it that way. Yes. Okay, let's try another one. Can you think of any perfect squares in 40? Oh, maybe one more thing. Let me make one more point. Notice how I was being careful here and I put a dot for multiply, then I just went, no more dots. I know, right? This means 4 times the square root of 3. I don't need that times. Just like in algebra, right? In algebra, you don't ever write 2 times x, right? If you had me as your junior high teacher and you were still writing 2 times x like that, especially if you didn't write curvy x for when you were doing algebra, I would do anything to break you from that habit. X has no place as a multiply symbol once you start doing algebra. And even in arithmetic, I make it kind of icky looking when I write it. You don't need a number between 2 and x to know that that's 2 times x. You don't need a multiplication symbol to know that this bracket is 2 times 5 plus 7, which is 2 times 12. You know that a symbol and then a bracket is multiply. And oh, remember what I said a few minutes ago? Radicals behave like exponents, like they do in this rule, but they also behave like brackets. And here we go. Here is my radical behaving like a bracket. I don't even need a multiply symbol, and I know that means 4 times what's in the bracket. In this case, what's in the bracket is the square root of 3. So there we go. So from now on, instead of bed mass, from now on it's bread mass. Because radicals behaves like both brackets and exponents, so we might as well put it in the middle. There you go, bread mass from now on. All right, let's do another example. What do I know about the square root of 40? It's got a 4 in it. And then that would be 2 root 10. What do I know about 72? Hey, it's got a 4 in it, higher. It's got a 9 in it, higher. It's got a 36 in it. This game only works if you find the largest perfect square factor. So that would be 6 root 2. What if you went, oh, I thought it only had a 4, and I thought, well, it's 4 times 18, which makes it 2 root 18. Aren't these two things the same number? Yeah, they are. Congratulations, they're the same number. But that's not the simplest number, because notice 18 still has a 9 in it. And the square root of 9 is 2. Or, square root of 9 is 2. The square root of 9 is 3. Sorry, it's been a long day. So notice I get there. You know what this reminds me of? This reminds me of grade 7. Remember in grade 7 when they told you to simplify this fraction? And if you said, oh, they're both even, I'll divide them by 2. And you stop there, you didn't get the right answer. But if you went, oh, I can keep going, there's still a 5 in there. Oh yeah, there you go. I should have taken out 10 in the first place. That's the same exact idea over here, right? It's like, oh, I didn't notice it was a 36. I thought it was only a 4. But then at this point, you have to recognize, oh, I can keep going. There's still a 9 in there. Does the logic of that make sense to you? All right. Now, how's our perfect cube knowledge? What's the biggest perfect cube in 24? 24 has an 8 in it. So again, this is the largest perfect cube factor. So that's the cube root of 8 times the cube root of 3, which is 2 cube root 3. Now you got to be careful when you write this down. Make sure that you can really tell that this 3 is the index of the radical and it's not an exponent on the 2. If you're not a very careful person the way you write, somebody might look at that and think you mean 2 cubed times the square root of 3, which isn't the same number, right? 2 cubed times the square root of 3 is 8 times the square root of 3. This is 2 times, I don't know, 1 point something. So there we go. All right, let's do another one with the cube root. What's the biggest perfect cube in 96? You know what? It's 8 again. Because 96 is in your 8 times table. It's 8 times 12. Are there any perfect cubes in 12? Well, let's see. It's got a 2 in it. No. It's got a 4 in it. No. That's it. So it's the cube root of 8 times the cube root of 12, which is 2 cube root 12. See, I actually make sure that my 3 is further right than like the imaginary plane of that index arm. And that's how I know. If I had wanted to draw 2 cubed times the square root of 12, I'd have for sure made it look like this. I'd have said 2 cubed times the square root of 12. See, I'd have made sure I'd even kind of almost have a little gap there. But no symbol, so I know I'm still multiplying. Got to be careful with your symbols in math. Anybody know the perfect cube in 108? Does it have an 8 in it? No. How do I know really quick it doesn't have an 8 in it? Cut it in half. Still even. Cut it in half. Oh, it's not even anymore. If you can't cut a number in half 3 times, it does not have an 8 as a factor, because think about it. 8 is 2 times 2 times 2. That's what makes it a cube. So what's the next perfect cube after 8? Well, 3 times 3 times 3 is 27. Are there any 27s in 108? You betcha. It's 27 times 4. If there's anybody sitting there going, I can't do that without a calculator, I got some really harsh news for you. Learn how to do this without a calculator, or the next test is going to be a really unfortunate time for you. Oh, and like I said, I don't need a decimal. I don't need a dot. I just need cube root of 4. There we go. 3 cube root 4. Again, if you don't believe it, you can always check. I mean, I'm not going to let you have a calculator on a test, but if you're doing your work and you just go, am I sure I did that right? Does, clear, does the cube root of 108 make the same number as 3 times the cube root of 4? Right down to the 10th decimal place, it most certainly does. Cool. So that was example 6. Like everything you learn how to do in math, we taught you how to square, then we teach you how to square root. We should be able to undo anything we do. We should be able to, we taught you how to distribute, we taught you how to factor. If we've taught you how to turn a radical into a simplified one, we should be able to start with the simplified one and make it an entire radical. An entire radical means that you have some sort of n as an index and x as a base, and the entire value of the number is contained in the radical. All right, so let's do, radical. Let's do what we did up ahead there, up above, backwards. So a mixed radical is the opposite. That's where you have some coefficient times a radical, where a mixed radical is the product of an integer coefficient, that's the a number, the coefficient, times a radical that can't be further. Now, see, is it further or farther? It's further because it's not an actual distance. That can't be further simplified. Grammar. So there we go. So for example, an entire radical might be something like, for example, the square root of 48. But the mixed radical, using the same example, is 4 root 3. Right? Why is 48 the same as 4 root 3? Because there's a 16 in there that kind of escapes the bracket and becomes its square root, which is 4. All right. Would it be wrong if you didn't use 16, like if you used 12 and 4? Well, here's the problem with 12 and 4. So let's go back. We had a question for one back here that I kind of skipped over. Meanwhile, back at 72, what if we'd have gone, well, first of all, yeah, what if we'd have gone, oh no, for 48. No, let's go back to 48. There we go. 48. What if instead of 48 we'd have used, well, 48 is 4 times 12. 4 is a perfect square, so it comes out as 2 root 12. See the problem? That's not finished, because I still know there's another 4 in here. Just like if I gave you the fraction 12 over 36 and you just cut it in half and said, there you go, it's 6/18, I'm done. No, you're not. That keeps on going and becomes a third. This keeps going because it's still got a 4 in it. And notice both roads lead to the same number. Does that answer your question? Somebody said, what if instead of the 16 you'd used the 12? Well, that's not the biggest. See, the 4 that you're thinking of here, this 4 is not the biggest perfect square in the number 48. 16 is. Okay? All right. So now let's go backwards. Write the following as a mixed radical. So if it's a mixed radical, that means that I want to turn it, oh, actually, hang on a sec. That's backwards. How about, okay, hang on. Can we fix the notes? The notes have a typo. Write the following mixed radical as an entire radical. Oops. Sorry. Oh, you know what? They're all wrong on this page. I totally forgot that there was a typo in the notes. So we'll fix that. Sorry about that. Anyway, 4 root 3 is the same as saying, okay, if this 4 is going to join the 3 in the radical, it has to become 4 squared. And that's going to be the same one we just looked at. 16 times 3 is 48. Okay, let's try the next one. We saw that one already. So again, this is wrong. It is a mixed radical right now. We would like to make it an entire radical. I guess I didn't need to wipe out the word radical. An entire radical. Okay, sorry about that. And I think, are the next two, do they have that problem too? You bet they do. Okay, we'll fix them in a minute. First, let's solve this. If the 7 is outside of the radical bracket right now, what was it back when it was inside the bracket? Well, it was 7 squared. What's 7 squared? It's 49. Quick, what's 49 times 3? Could you do 50 times 3? Sure, it's 150. Good, now take away a 3. This one's easier. 5 root 2 is like saying 5 squared times 2 as an entire radical, which is 25 times 2, which is 50. Any questions on those two? All right. Now let's try it with cube roots. And again, this is supposed to be an entire radical. An entire radical. So sorry, somebody typed that wrong. Wasn't me. All right, now this 2 has to join the 4 as the perfect cube that it was before it came out of the bracket. Well, 2 cubed is 8. So this is like saying the cube root of 8 times 4, which is the cube root of 32. And 3 times the cube root of 3, what was the perfect cube of that I cube rooted to get to 3? It must have been 27. And 27 times 3 is 81. So this is the cube root of 81. And there we have it. That's the 4.3 lesson. Now, I didn't give you any time yesterday to work on the 4.2 homework. So you can have the rest of this class. And actually, I don't think I'll do a lesson tomorrow. So we have kind of a bigger assignment here. We want lots of practice on the stuff that we've done in the notes here. So the assignment is, let me just go back to the blog here for a sec. There's the blog. So the assignment is the stuff I assigned yesterday, 3, 4, 9, and 12 from page 211. And then the stuff that we covered at the end of today's, or the beginning of today's lesson is also here. The end of today's lesson's right there. So the 4.3 stuff is right there. Questions, page 218, questions 4, 5, 10, 11, 12, 17, 18. Okay, and have I updated that? Yes, I have. Okay, so there we go. So I'm going to stop the video now, and I'll post it for anybody who